Can everybody hear me in the room? All right, cool. So there are a few people still coming in. I guess we can start, though. So hi, everyone. My name is Kostas, and welcome to Flink Forward 2015, which is the first conference on Apache Flink. So I'm really excited to see faces that I know, and also a lot of faces that I don't know. So this conference is sponsored by Data Artisans and KPMG. Before we start with the first keynote, I would like to give you a little bit of practical information on how you move around the conference and so on. So, number one, hopefully everybody has registered already. If not, the registration is in the room you came from, is at the entrance. You can register all day, so you can go and just pick up your badge. I understand that some badges did not include the affiliation for some reason, so take a pen and write it if you want, or write anything else you want on there. The information point and the registration is always staffed, so you can always go there if you have a question. Our Wi-Fi is called Flink Forward, and it's not password protected, so you can just connect. And if you're feeling social, our Twitter hashtag is hashtag FF15, and you can follow Flink Forward on Twitter. Very important, if you need any kind of help at any time, just try to locate a volunteer. You can spot the volunteers because they have a pink badge instead of a yellow or a black one. We have 3 parallel sessions in this conference, 2 sessions with talks and 1 session with training. But don't worry, if there are 2 talks that you would like to see, everything will be recorded and will be made available online after the conference. And this also includes the training sessions. So if you want to go to the training session, so you can also watch the training sessions later on YouTube. This is a small map of the rooms that we are using. So we are at the red room right here, right now. This is called the Kessel House. And 1 session will be here. The other room is called Machinen House, and it's just on the back of this one. So if you follow the stairs that go up and go down again, you can reach it, or you can go out and go around. So try to not disturb the talks when the speaker is talking, and move between the rooms from around if possible. And the training is across the street, so if you go out and cross the street to the building, there's a room that is called Moon Lounge. There's signage everywhere, so it should be easy to find. If you have any questions, again, you can just locate a volunteer. Now, I'm extremely happy that we have all these great talks here from a large variety of organizations, large companies, startups, universities, the whole spectrum. So I want to use this moment to basically thank all the speakers. So thanks a lot for coming and speaking. Now, all right. So the title of this talk is Apache Flink from incubation to Flink 1.0. This is very general. We want to talk to you about a few things. Who are we? I'm Kostas, and later in the stage, Stephan will join me. We are the co-founders of Data Artisans, the Berlin-based company that was founded by the original team that developed Flink. And we continue to contribute to the project and push the project forward. And we want to talk to you about a few things. Number one, we thought that it would be fun to take a small trip back to memory lane and see where we started. So, from incubation, when Flink entered the Apache incubator, until now. Then we want to basically tell you where we see Flink within the greater changes that are happening in the data infrastructure space. And then Stephan will come and talk to you a bit more about the upcoming release of Flink, Flink 0.10. Now, Flink 0.10 is worthy enough because it's not just another release, but it actually brings Flink to a point that it can really serve the next generation of data analytics use cases. And finally, very briefly, we'll talk about our view of where we see the project going forward towards the 1.0 version and beyond that. Now, starting off with a bit of history. So, some of you might know that Flink was originally called Stratosphere, and it entered in April 2014 the Apache incubator with that name. So that was this point here. 3 releases later, and actually a few months later, only in December 2014, the Apache Software Foundation decided to make Flink a top-level Apache project, so graduated from incubator. And it is very interesting to see the difference between Flink when it entered the incubator and at release 0.9 that was done this summer. So at incubation, Flink was basically a core engine with a few deployment options and an API. And release 0.9 really elevated Flink from an engine to a more complete framework, so it added a bunch of different APIs with which you can access the system, covering a broad spectrum of use cases, patch analytics, streaming analytics, machine learning, and so on. So we really see a diversification of the project growing a lot in scope. And now we are heading towards the 0.10 release. Now, this code growth was also accompanied by a tremendous community growth. So by now, Flink has well over 120 contributors, probably close to 140, which places it as one of the biggest and most active projects in big data in the Apache Software Foundation. So that is great, and this community continues to grow. The next thing is that this community is truly global. So while the origins of the system and the project are here in Berlin, by now there are people that are contributing code and using Flink all around the globe. And one data point here is Flink meetups. So this is a map of Flink meetups around the world. They span 3 continents, North America, Europe, Asia, a bunch of cities, including Berlin, Stockholm, San Francisco, and so on. So if you don't have a Flink meetup where you're located, please go and create one. So it's a lot of fun. It's a little bit of work to organize a meetup, but we have seen, for example, recently a Paris meetup for Apache Flink starting and in a matter of days or weeks reaching 100 people. And also Flink got quite a bit of attention in the media. So this is a bunch of logos from blogs, media outlets, and so on that have written about Flink, company blogs, and so on. And very recently, Flink was one of the systems that won the BOSI Award, so the best in open source big data projects. Good. That brings me to the next thing that I would like to talk to you about, and I'm calling this the streaming era. So I believe that this is where we are right now. If you have never heard the word streaming before, very briefly, the easiest way to explain that is the following. There are basically 2 kinds of data applications. There are the data applications where we have a bunch of data and we want to do some analysis on that and get a result back. For example, you collect a bunch of data and you want to generate reports overnight for the management to see during the next day. So these are usually called batch applications, or they come with many names. And by now, we believe that these are well served by a variety of tools in the open source space, including Flink. But there is another half in the bigger picture, and these are event-based or streaming applications. These are very, very different. So an example is, for example, a bank wants to react on a credit card transaction to see if there is a possibility of fraud. So these kind of applications were until now not well served by the open source systems out there, and they indeed need completely new systems to be served well. And the good news is that there is actually a new breed of systems that is out there and can serve those applications very well. So we call this streaming, and I believe that streaming will be the biggest change in the data infrastructure world since Hadoop. So it will completely change the way we think about data, from data production to data movement to data storage to analytics. Yeah, and I cannot stress this enough. And there are a bunch of reasons for that. 3 reasons are here. So number 1, streaming promises to radically simplify the way we architect our data infrastructure. And this is also connected with broader trends that are happening, such as the move to more, let's say, microservices-based organizations. I will talk more about that later. Number two, new applications. So the Internet of Things is rising, connected devices that continuously collect data and push it to the data center. These applications actually need stream processing. They cannot be served well with the old systems. On-demand services like Uber and so many other things that we're seeing in our everyday life. These create applications that need to react to events as they come and not collect some data, do some analysis, get back. And number three, and that is also very interesting, streaming promises to not give you one more system to manage, but actually promises down the line to completely subsume batch. So streaming is a proper superset of batch processing, and with a properly designed stream processor, you can cover both your new streaming use cases and your older batch use cases. So batch is not going anywhere, but it can be served equally well by the new systems. So this is an example of how streaming can radically change the way we think about data infrastructure. So we are moving from a world where a bunch of applications coordinate using a global view of the world that is typically kept in consistent storage. So basically, we're trying to model what is the current state of the world, of the whole world right now, put that somewhere, and then every application needs to go and get what it is interested in. So an interesting move away from that is where its application, where there's no longer a global view of the world. Nobody knows how the whole world looks like right now. What we have is the history of the world, and this history of the world is represented in the form of an event stream. And applications actually maintain only the little part of the world that they are interested in. So one application may be interested in data in Europe, the other application may be interested in data in the US. So then we are moving basically from the problem of maintaining consistency in a consistent store to the problem of actually moving these event streams between applications. And moving these event streams consistently and fast is exactly the role of a stream processor. So really, in this new world, the stream processor forms the backbone of the data infrastructure. It is a very crucial piece in the infrastructure. Now, if streaming is so great, the next question is, why haven't we been doing this forever, right? Well, the answer is it has a few phases. So first of all, some people have been doing this for a while. And some of the open source streaming systems that we know came out of companies that have been doing streaming for a while. For example, Storm out of Twitter. Second, a stream processor is honestly harder to engineer and build than a batch processor. So for a long time, the open source space lacked stream processors that were as mature as their batch counterparts. So a lot of older stream processors, for example, lacked inconsistency. They provide weak consistency guarantees. Others had problems with maintaining throughput under back pressure, and so on and so forth, right? So the maturity was not there, or they lacked the nice APIs, the feature set, all of that. So this led basically people that actually had streaming use cases to do one of three things, or even a combination of these three things. Number one, lots of companies actually build in-house solutions. And as I said, some of the open source systems that we know nowadays are a result of open sourcing these in-house solutions. More often, these in-house solutions were very tailored to the use case. Number two, people have been using or abusing batch processors to do stream processing for a very long time. So if you have ever seen in your company a directory of files where each file is essentially a timestamp, a day and a time of a day, and there are thousands of these files, this is basically, in the streaming world, this is what we call windows, right? And you can do that in the application rather than creating files. And third, it led to things like the Lambda architecture, where you have a stream processor and a batch processor living alongside each other, the batch processor doing the heavy lifting, and the stream processor basically picking up on the new arrivals, but not providing the accuracy that the batch processor provides. Now, what we're happy to tell you is that this is no longer the case. So streaming technology has matured enough that there are systems out there that match the older batch systems in maturity, in feature set, in consistency, and so on. And one of these systems is actually Flink, especially with the additions that are scheduled to the upcoming release, Flink 0.10. So right now, the Flink community is preparing to release 0.10. While the previous release, 0.9, was what basically elevated Flink from an engine to a more complete framework, what 0.10 brings is a ready-to-use streaming system, a ready-to-use stream processor that can really serve as the backbone of all analytics, and it can replace also batch use cases very, very well. Stephan is going to dive into the separate features in 0.10 that actually make this possible. What I wanted to say now is that, especially exactly because of the significance of 0.10, I actually wanted to call this Flink 1.0. However, the Flink community decided to do 0.10 and head to 1.0 later, so that's where we are. So I really view this upcoming release as a preview to Flink 1.0. And the good news is that not only Flink is maturing, but also the greater ecosystem around the streaming technology is maturing very, very fast. And a few examples of this are, for example, Apache Kafka, which came out of LinkedIn. It's now used very widely. This is great news for Flink because Flink is using Apache Kafka for stream durability and for replaying streams. Right? Another extremely interesting technology that has matured, so it's now generally available, is Google Cloud Dataflow. This is the system that we will hear in tomorrow's keynote. And that is something that I find extremely interesting because Flink and Dataflow actually share a lot of commonalities. So for example, with Flink 0.10, the windowing system and the underlying programming model of Flink and Dataflow are very, very, very close together. Yeah? And in fact, we as data artisans have also partnered with Google to deliver Flink runners for Google Cloud Dataflow. So you can run your Dataflow programs on Apache Flink if you don't want to use it in the Google Cloud, if you want to use it on Yarn or in some other cloud provider. So what is interesting here is that we see again this pattern of a technology that is originating at Google. So Dataflow is based on years of internal use at Google and replacement of older systems inside Google, including MapReduce, for streaming use cases. So while the world was jumping on Hadoop, Google was very early moving on to data streaming for many of its problems. So we see a combination of a technology that originates in Google and an Apache project that resembles this technology. So we have seen this again and again with MapReduce and Hadoop and so on. The different thing here is that Google Dataflow is also available to the public as a service. It's not only internal, as MapReduce was. And the two systems are actually working together to make it possible to run one on top of the other. So it's going to be much easier for users. So just before I give the stage to Stephan, who will dive into Flink 0.10, to summarize. So streaming is happening. So this is going to be the next big step in big data infrastructure. If you're not doing this right now, you are going to do this in the future. So it's a good idea that you start thinking about this. And with Flink 0.10, the community is bringing a stream processor that is ready to use and really serve as the backbone of your data streaming needs. All right.
Okay, thanks, Kostas. Yeah, my name is Stephan. I am one of the co-founders of Data Artisans as well, and one of the original crowd that worked on, back then, Stratosphere, the project that came Apache Flink. So I'm one of the people who has been with this Flink project for a very long time, since the first Lano code, actually. And yeah, as Kostas said, I would like to talk with you about Flink 0.10, the upcoming release. And Kostas mentioned this, it's not just another release, we're not just telling you, okay, yeah, something is going to come up right now as it does every few months, But there have been a few significant steps forward in this upcoming release, especially in the area of data streaming. And I would like to show a few select features of what is coming up and put them also into the broader context of the streaming vision that Kostas gave. And yeah, so the first thing I would like to talk with you about is actually the data streaming API as we reworked it, because that's probably the first thing you're going to ever get in touch with if you're trying out the new release of Flink for a data streaming use case. So in 0.9, we added the data stream API to Flink. Flink has always been a data stream processor at its core, and with 0.9 it actually added a very nice high-level API to surface this to the user. And over the past 3 or 4 months since we published this API, we actually we worked quite a bit with it. We took feedback from users, and we took, admittedly, a lot of inspiration from the work of the Google Cloud Dataflow team, as Kostas said, and mixed this together and basically reworked the API, especially the windowing system, to its new state. And the goal that we had in mind when we were doing this is the following. Most people by now know how to use batch processors, and especially with the nice high-level APIs like, for example, Flink or Spark or Scalding, so bring them. And in the data streaming space, we thought that it would be nice to make the transition from batch to streaming very smooth. And the main thing that people actually have to start thinking about when they move their programs from batch to streaming is the notion of time. So where if you run a program over a data set, it really doesn't matter whether an element in the data set is at the beginning or at an end. In the data streaming program, it has an inherent meaning if it is at the beginning in the stream later. Elements have time, either explicitly attached to them or implicitly by the time that they arrive. And so the first thing that you always have to worry about if you start working on streaming is actually time. And the extent to which you deal with time can actually be, you can deal with it in a very simple way. Just say, give me some windows over my stream in order to let me do my groupings and operations. Or you want to deal with time in a very sophisticated way. You want to deal with out of order, with early and late arrivers and everything. And the idea of the streaming API, the reworked one, was actually make this very easy and give an easy entry point to people who just want to deal with it in a simple way and make it very extensible for people who want to deal with it in a very sophisticated way. So I think what the API looks like is best illustrated at the example of a bit of code. And this is a highly simplified use case, so it actually fits on a single slide. The use case is a system that receives events from traffic sensors. So the core event that we're dealing with is very simple here. It's just an event that has a location where the sensor recorded something and a number of vehicles that it recorded. So think about a sensor that is attached to a traffic light or one of these induction loops on the road. And once we create such a data stream, the first thing is we just filter something. We just filter it by saying, okay, let's only look at events from intersections. And this is pretty much like in a batch API, a one-liner. The next thing that we want to do is compute some statistics over this data stream. Basically, like we do in a batch API, a group by and then aggregate. And like I said before, in a streaming system, you then have to start worrying about some form of windowing. So if you, for example, say count the number of elements in a data stream, that doesn't really work, right? The data stream is infinite; it doesn't have an end. So if you want to compute anything over this stream, you have to sort of give it a frame of reference that you want to refer to. And in this case, we take the simple-most frame of reference, which is time. We make a time window of 15 minutes that computes every 5 minutes, and this just sum up the elements in there. So what this is going to give us is a sliding statistic over the data stream. Now, if we want to make this a little more event-driven, and for example say, these statistics are nice, but in case we have, let's say, a traffic spike, we actually want to react to it instantly, not just wait for the next statistic to arrive. So what we can actually do is we can, on top of this window, register additional things like a trigger. So we tell the system, okay, as soon as we've seen more than 200 observations, actually trigger an event early. Don't even wait for this time window to expire. And this is, for example, one of the new additions to the streaming API. And if you're if you're looking to learn more about this, there's a talk later tomorrow by Alyosha that is actually going to describe how all these windowing triggers. There's a lot more. There are like multiple windows assigners, global window assigners, evictors, and so on. How they all play together and actually give you an incredibly powerful system that can give you from anything like super simple time windows to very sophisticated data-driven windows, processing time event time-driven windows. It allows you to scale from very simple to very complex use cases. So that is one of the nice things we added. Another thing that came up between 0.9 and 0.10 is actually the handling of state. And these lines may look a little complicated. Bear with me for a second. What they are actually illustrating is that the streaming API can actually help you to just manage the state of your application as well. So on top of computing the statistics with the windows over the data stream, we actually apply the result of them to a machine learning model. And now, interestingly, you can just take this and pipe it to an extra system and have this there, but you can just also let Flink do this. Define this model to be stored as part of the streaming program, as part of the state. Apply it to every event and update it with every event. And the benefit of doing this is actually that Flink takes care of the consistency of everything. So when it snapshots the streaming application, the inputs, the windowing computation, the model, it will actually take care that these all reflect a consistent state of processing. So it's actually very possible to move stateful computation and state into the streaming program. And actually by that coming to the point that Kostas mentioned, to have multiple individual models of the world that the stream processors keep consistent. That's one thing that we're actually fairly excited about. The next thing is a set of applications that is, or is a new set of features that is maybe best explained with a set of applications like Internet of Things and mobile applications. And that is actually, it's a feature set that what we believe is going to be very crucial for this set of applications. So, I think it's best illustrated at a simple use case as well. And let us assume a setup where we have a couple of sensors that are producing events, sensor records, putting them into a queue, let's say Kafka, and then we're analyzing or reacting to the events with a streaming system like Flink. What we see in practice is actually that these devices that publish their data to the queues, they don't always do this at the same speed. They're not even always connected. So let's assume that all these 5 events, all these 5 sensors actually create a burst of events. And as it turns out, 3 of them are connected, and 2 of them, the cell phone doesn't have reception right now. The sensor just disconnected to save some energy or so. And the sensors flush their first set of events to the queue if they're connected. They're holding on and just storing them locally if they're not connected. We have a second burst of events that the sensors produce. They're putting them into the queue. And at some point in time, the 2 others regain their connectivity. They actually publish the next set of events. And the result of that is that in practice, we actually see that events generated by these kind of applications come highly out of order, right? So in the queue, the position of the event in the queue, or the time when the event occurs in the queue, has actually nothing to do with the meaning of the event with respect to the time that it occurred. And that is actually that poses quite a challenge to the application in many cases. So what do we do with these events now? I think there are more or less 3 different categories of analysis that you do on top of these events. First of all, there are single instant event at a time responses to each individual event occurring. You see the event, and with very low latency, you want to react to that event. The next thing that's probably very intuitive is the one at the very bottom, event time windows. You actually want to group the events and work with them with a frame of reference as the events were actually occurring, right? So let's assume we want to correlate GPS traces from different mobile phones. We don't want to do this by the timestamp with which the events occur in our system. We actually want to do this with respect to when they were occurring. So we're building what is called event time windows over these events, or we're joining them on event time. And the one in the middle is, interestingly, the thing that most systems do today is windows over arrival time. So you basically set a trigger and say, I compute something every minute. And this minute actually refers not to when the event occurred, but when the event was observed by the system. So all of these things are actually valid things to do, right? Instantly reacting to an event, reacting with a medium to low latency with windows based on arrival time, and computing with strong semantics computations over the data stream. All three of them are very valid. There's not one that is, if you can do this, you don't need the others anymore. Most applications, sophisticated applications, will do a combination of all of them. And this is something that, that is actually now possible with Flink's new API. The introduction of event time windows, processing time being in some sense a special case of event time, meaning the times are just timed by when they arrive in the system. And instant event at a time is what you can always do, and as long as you don't want to group the records or so. So to the best of my knowledge, Flink is actually the only open source system right now that has support for these three types of applications. Google Cloud Dataflow was a big inspiration for us to do that. I think you can actually express these things there as well. But if you want to run them in open source, I think Flink's the only system right now that has incorporated these concepts so far. All right. So this is the second, more or less, application-centered feature that we were very excited about that is coming up. The next thing, of course, all of this is only valuable if you have a system that is actually doing this reliably, that is guaranteeing you consistency throughout the computation, that is going to stay available in case of errors. So with 0.9, we introduced for data streaming a new fault-tolerant feature, which we call asynchronous barrier snapshots, or distributed checkpointing of streaming data flows. It's a very cool technique, actually. I think it's also fairly unique in the open source space there, that you basically take the streaming topology and you don't subdivide this processing steps into something like mini batches, or you don't run transactions for elements as they're exchanged between operators, but you just let the streaming system flow, and in the background you inject certain coordination barriers that draw snapshots of the state in the background and thus coordinate the taking of distributed checkpoints of the data flow. It's a very cool technique, and it's actually very important for this vision of data streaming with this high flexibility in Flink, because the one important thing is that this checkpointing does not in any way interfere with the way that windows can be computed, that state is maintained, so it allows you absolute flexibility in your definition of windows. It doesn't restrict you to some ground granularities or anything. So windows, triggers, everything can come independent of any checkpointing settings, and that is super important. And as I said, the first version of that was introduced in 0.9. We hardened it and integrated it with more data sources and sinks in 0.10. The next feature that is coming up in 0.10 is actually high availability of the Flink master. So with that feature, there's going to be no single point of failure in Flink anymore. So you can really run it in a highly available fashion if you have either Zookeeper running and you can run multiple standby masters, or if you're running a highly available installation of Yarn, you can use it in both settings. All right. Other than implementing new features, what we did quite a bit in the past months was also analyzing a little bit what Flink can do, what is the performance, and trying to figure out what are performance bottlenecks, why is the performance like that, and when you talk about performance in streaming systems, you typically talk about two numbers, throughput and latency. And I have actually two charts on this slide, one for latency on the left and one for throughput on the right. And let me actually go through them just very briefly. So on the bottom right is a throughput chart of Flink for an admittedly quite simple job. You have a streaming event source, you take the events, you route them based on a certain event classifier, you group them and aggregate them. So it's if you wish, something like the word count on streaming, only on continuous streams. And the throughput that Flink is getting there is actually, it's impressively high, I think. And what's even more interesting is once you start activating the fault tolerance mechanism, you see that the throughput takes a slight dip, but it's actually not a lot. So this is kind of a nice point for us to see that this model of coordinating checkpoints really with injecting metadata events and barriers into the data stream rather than subdividing it into batches or running transactions is actually a technique that really goes well with high throughput systems. The other chart on the left-hand side is a diagram that contrasts what kind of latencies can you get and what kind of throughputs do you get with these latencies. So, not sure how well you can read it, so let me just briefly explain it. there is a knob inside of Flink that allows you to trade off throughput and latency. So if your application requires an ultra-low latency, it can tell you, make sure the event never is stuck longer than so and so many milliseconds in Flink's network stack. The lower you tune that number, the more you take a dip on throughput, and the higher you let this number be, the more throughput you can actually get. And this chart actually nicely shows that if you're willing to live with a latency of, let's say, around about 50 milliseconds, you actually get almost the full throughput. If you really want to keep your latency below 10, 20 milliseconds, you will actually get a dip in throughput, but it's still a pretty decent throughput you can get with that. And the recipe that we figured out and how to do this is this formula at the top. Using a continuous streaming system like Flink, but not really operating internally as at an event at a time model, but doing something that we call latency-bound buffering, and doing fault tolerance by distributed snapshots rather than acknowledgements, transactions, or mini batches actually gives you this nice combination of high throughput and low latency. All right. We've been talking a lot about streaming so far. Admittedly, most of the people that have worked with Flink since the early days will probably have worked with the batch APIs because they've been there much longer. They have actually more libraries because we've worked with them for a longer time. And how does streaming and batch relate in Flink? Kostas already said it in his introduction that streaming is really actually a superset of batch processing, and this is not just theoretically so, it is really actually very practically so in Flink. Here's an example of how you can actually write a batch word count in the data stream API in the new one. It looks very similar to the original word count program in Flink's batch API. The only difference that we do here is we sort of have to tell the streaming system, if you group by an aggregate, what is your frame of reference? And we basically tell it everything, right? We assume the stream is actually bounded. It is a set of files. So take the global window and trigger it only once you reach the end of the stream, and boom, you have a batch word count. Now it's a little awkward to write it like this, and of course we're not ditching the dataset API and ask people to now write your stuff in the data stream API. So the dataset API still exists, and word count in the dataset API looks like this. It's not too different. Now, it is not really just syntactic sugar that we say a dataset API. It's just a data stream API which has some implicit notion of a global window or so, and everything else is the same. You can, in theory, do exactly that, and that is what people have come to call the Kappa architecture. It is work, but you can actually do a little bit better than that, because if you take a system that is super generic, if you take a windowing system that's designed to be as flexible as the one in Flink, and then you're actually not really using it, but you're just saying, okay, take everything. That's not going to be super efficient. So the batch API in Flink is actually not just a syntactic sugar over data streaming, but they share a large common part in the core, the streaming data flow runtime, with a lot of primitives like streaming data movement, stateful operations, and so on. But whenever we submit a batch program or a data streaming program, what we actually do is we slightly parameterize them towards the use case. So scheduling is done slightly different for batch and streaming programs. The streaming programs draw these periodic checkpoints, while the batch programs say, well, if my input is a file, I don't really need to checkpoint this. I can reread the file, right? So I can save myself the checkpointing. So not only the system underneath executes the batch and the streaming program slightly differently, but also when you come from the APIs to the streaming program, we follow slightly different translation steps. So if you're working on finite data sets, you can make a few more assumptions. So that's what led us to plugging in the Flink optimizer that deals with dataset programs, tries to reuse partitioning, sort orders, optimizes iterations. On the data streaming side, the windows are probably the most complex thing. So the most important thing to work there is look at the windows and try to make sure that you pick good implementations for the combinations of triggers and time, windows, and so on that you choose. So the result is that Flink is not actually just a streaming system that can also do batch. It's actually it's a full-fledged batch processor. It's a very rich batch processor. It has a big set of APIs on top of the big set of libraries on top of the dataset API, and I've been asked a few times, yeah, of course, you can do that. I mean, I agree in theory, stream processor can do batch processor, but wouldn't a dedicated batch processor be always better at batch processing than a stream processor doing stream processing? And interestingly, actually, no, not necessarily. There are a lot of concepts in data streaming that actually help batch programs as well. So this is, these are two figures taken from the blog of Dongwon Kim, who's giving a talk later today on a comparative performance evaluation of Flink. And these are just two data points, a TerraSort benchmark and a join benchmark. And it actually turned out that Flink was the fastest system in both of them compared to dedicated batch systems, and these are dedicated batch programs. So yeah, for more information, I would say visit Dongwon's talk. But it's actually an interesting testament that building batch on top of streaming is not a weird idea. It's actually, in my opinion, a pretty good idea. Okay. I'm almost at the end of the presentation of this new release. Kostas mentioned that we're seeing streaming not just as another part of the analytics infrastructure. You have a queue, you consume some events, and you compute some analytics over these events. But it's actually going to be much more crucial. It's going to be one of the central infrastructure pieces. And for a system to be a central infrastructure piece, it has to play well together with the other pieces of the infrastructure. So what we've been seeing over the past month is actually more and more people contributing connectors, so working on letting Flink work with other systems. And this is what this picture shows. So the left-hand side is a set of, by the way, it's not by no means complete. It's just a few figures that that Kostas and me that came to our head when we were thinking, okay, let's make a slide with the systems that we integrate with. So I'm pretty sure I forgot quite a few. So on the left-hand side is the data, the file systems. In the middle, the databases. At the bottom, the message queues. At the top, that Flink can consume data from. On the right-hand side, the indexes, message queues, databases, file systems that it can write data to. On the bottom, the set of deployment options, if you wish, that you can run Flink on. So Google Cloud Platform, it's integrated with the tools there, of course, on top of MapReduce, Yarn, Docker, or Amazon Elastic MapReduce. There's a pull request with Mesos that is still under the works. On the top, you actually see systems that can execute their programs on top of Flink. And interestingly, they're also batch and streaming systems. So you can execute MapReduce functions on top of Flink or cascading data flows. There's, as of 0.10, coming up a small compatibility API for Storm and a runner for Google Cloud Dataflow. And it's another testament, I think, to the flexibility of a stream processor, having data flows and batch processing systems, so streaming system and batch systems on top of Flink. Yeah, and basically the final slide for the release is monitoring. So one of the requests we've been getting a lot is please add a bit to Flink's monitoring. If it is going to be a crucial piece of the data center infrastructure, it has to provide monitoring capability. So what's also coming up in 0.10 is a reworked web dashboard that is going to show you live metrics like how is the system consuming bytes and records and producing them. You can plug in custom accumulators which get updated in real time. And something that is actually a little bit hidden, but I think very valuable, is a monitoring REST API that we're exposing. So you can more or less connect custom monitoring tools to Flink if they are able to retrieve their metrics by issuing REST requests and receiving JSON responses. So that's a good building block for actually integrating it with monitoring infrastructure, or just for you to go and understand what your jobs are doing. So. There was a lot of material, so let me sum it up in basically 5 points. The 0.10 release had a lot of focus on operational readiness, high availability, monitoring, integration with other systems. We introduced first-class support for event time, which is crucial for these applications like mobile Internet of Things when we see events coming out of order. And that surfaced in a refined data stream API that is designed to be easily approachable, but also scale to complex use cases. All right. At the end of his talk, Kostas mentioned that he wanted to call Flink 0.10 actually Flink 1.0, and yeah, Flink 1.0 is going to be most likely a very close successor to 0.10. So what the community is going to do is take actually 0.10, do thorough testing, and focus on bringing the machinery in place that can actually guarantee API compatibility across the 0.x releases. So making sure that we define explicitly what is part of the public APIs, what is part of the internal APIs, and making sure that we have mechanisms in place that we notice once we break the compatibility. That is probably the most important thing that is between 0.10 and 1.0. The features in the engine are getting more and more complete. So after 0.10 and 1.0, a good focus that we want to put is actually making sure that we focus on usability features. And usability features are tooling, are in many ways connectors to other systems. And the engine features that we'll work on are probably going to be mostly elasticity and memory management. But like I said, the big focus is going to be on connecting to more other systems and usability. And with this, we're actually done. Enjoy the rest of this conference. I'm going to give the mic back to Kostas, and I think we're going to have a set of lightning talks now.
All right, so the next session is a set of lightning talks by some people that want to advertise their Flink use case before their main talk. So I would like to ask the speakers of the next section to slowly start coming up. And I guess until then we can do a short Q&A. So are there any questions for the first talks? Yeah. Sorry, can you repeat that? So the question is whether the Python API documentation in the dataset was updated, I guess, recently. I guess the answer is not really. So the focus of this release was mostly on operational streaming and making streaming extremely powerful. Python is coming after that.
I think that a few committers that work on the Python API are here. They're probably better suited to answer that question. For example, I'm not sure if Chesney is going to be here, but definitely Max and Fabian have been in touch with that a bit, Alyosha. So look for the people with the committer tags on their badges, and for a guy called Max, Alyosha, or Fabian, I think they probably can answer that question better. They were actually working on this. I think there was another question. There was another question here in the front. I think Martin, no?
Yeah, I just wanted to ask, what's the release schedule? So when is 0.10? What do you think when is
Okay, so what is the release schedule? That's a nice question. Okay, so I mean, you can never pin it down to a single day, right? So 0.10, the features have been merged. It's basically testing now, and we've updated most of the documentation as well. It's testing and voting on the release candidates. I would say give it a week or two, hopefully less. For 1.0, I mean, this is a decision that not we here make. It's a decision made by the Flink community. But I think most of they're basically in agreement that 0.10 is a very good step towards 1.0. And like I said, the most crucial thing that is missing is defining clearly what is part of the public API that we want to guarantee backwards compatibility for. So that is not actually such a big amount of work. So I would assume that it's going to be, a few weeks to 1 or 2 months after 0.10. It should not be more. All right. There's another question in the middle. Oh, a few more there in the middle. By the way, do we have a mic that we can give to the people that ask the questions, or should we just repeat the questions? Just repeat the questions. Okay, just ask, we'll repeat them. Ah, yeah, okay. Can we bring back the slides? I don't know. Okay, so I think I can answer it like this. These figures were taken from a blog post that we published a while ago. So this blog post actually says exactly what kind of configuration the hardware was, what kind of configuration the events were, and so on. I think it was a cluster of 30 nodes or so with all in all 120 or 160 cores. I don't remember exactly. The events were in the order of I think low kilobytes. So they were designed to be small events to not, test the TCP protocol, how fast it can transfer a chunk of bytes, but to test the mechanism that, does the accounting of events and so on, with how many events can it keep up. Did that cover it, or? Okay. So events, low kilobytes, clusters, 30 machines, 120, 140 cores, I don't know. Something around that. It's in the blog post, the details, definitely. There was another question, I think, right next to you. Okay, go ahead, please. Can you repeat this? Is Flink a good entry point for someone? Yeah. No, I would say it's a good starting point, right? The APIs in Flink are as easy as they are in any other system. So the available primitives that you have, especially in data streaming, are, I think, easy and powerful. So you'll probably find it easier to use Flink streaming API than most other streaming APIs. And I would say that for the batch API, it's definitely on par with other systems as well. So it's a good candidate to start, in my opinion. Can you repeat the question? Yeah. Actually, the question was, did we do some benchmarking against Storm? Yeah. So the figures you saw on the slide where I showed performance numbers, they were actually Flink against Storm. Yeah, it was this job where we had, like I said, where I said this is a little bit like MapReduce word count, but in the streaming API, you basically have events. You group them on something. You aggregate them as they come over time. The two bars on the bottom that you see here is actually Flink, the throughput. The one at the top is actually vanilla Storm without any tweaking or without Trident. You can get the bar actually. You can get it higher if you use Trident. But this is roughly the comparison. So by the way, this is, I think, both systems with in their vanilla configuration. So out of the box experience with both of them.
All right. Thanks a lot, everyone. So the next session is going to be a lightning section where speakers will introduce their talks in 5-minute windows, if you wish.